So we're going to talk in 3.3 about the product and quotient rules. We have talked a little bit about how we have to be careful that we don't know how to differentiate the product of two functions nor the quotient of two functions yet. So first, let's just see why our intuition does not serve us well. So we're interested in finding the derivative of two functions. So I'm going to say in this case, we want the derivative of f of x times g of x. Now we know that we don't really need to treat that as a product because we know that if we take x to the third times x to the fourth, that's really x to the seventh, and we can take the derivative of x to the seventh using our power rule and get 7x to the fourth. But let's use this to see why our intuition is not correct. That is, this is not going to be equal to the product of the derivatives, which is what most people want to try to do. Because if we took the derivative of x to the third, we'd get 3x squared. And if we took the derivative of x to the fourth, we'd get 4x to the third, and that would give us 12x to the fifth, and we can see that is not what we should be getting. So, surprisingly enough, it turns out that what we do for the derivative of the product of a function f of x times another function g of x is the first f of x times the derivative of the second plus the second times the derivative of the first. Now, if we're doing this in class, I'm going to have you recite this over and over again because hearing your own voice helps it stick into your brain better. So there you are, sitting there by yourself. You can do this and just make sure nobody's in there that can hear you. And I think you've lost your marbles, but it is the first times the derivative of the second plus the second times the derivative of the first. The product rule is the first times the derivative of the second plus the second times the derivative of the first. Let's see how it works in our example here, and then you can trust it, hopefully, in the future when we can't really multiply these together to find their derivative. So if we take the first, x to the third, times the derivative of the second, that's going to be 4x to the third, plus the second, x to the fourth, times the derivative of the first is 3x squared. So that's going to become the first two, that's going to be 4x to the sixth. Did I do that right? And then we're going to get 3x to the sixth. I didn't do this one right up here. You guys were supposed to have stopped me. That's not 7x to the fourth. It should be 7x to the sixth. It's hard to get the right answer when the one you're comparing it to isn't correct in the first place. All right, should be 7x to the sixth. Now that I have the correct answer to check it with, we can see that it is in fact correct. So let's do this with a couple other examples. So let's do something like, say, f of x equals x squared e to the x. You may want to pause the video and try it on your own first. But the derivative, and I would recommend you say it out loud as you do it. So it'll be the first times, and the derivative of e to the x is e to the x, plus the second times, and then the derivative of x squared is 2x. So usually what we do here is bring that stuff that's out in front of the exponential so it doesn't look like it's somehow mixed in there and part of the exponential. So we would generally write that as x squared e to the x plus 2x e to the x. So if we do something, now this one's a little artificial because we don't have to do this using a product rule, but we don't have a whole lot of different functions to use as functions that are factors, things that are being multiplied. So rather than multiplying this out, which we certainly could, Let's do this as a product rule problem. So if we take the first, that's the x cubed plus 3x squared plus 5 times the derivative of the second is going to be just 3 plus the second, 3x plus 7 times the derivative of the first, which will be 3x squared plus 6x, and then the derivative of 5 is 0. We could multiply that all out, but that's not really the point of this. We just want some practice doing the product rule. Okay, so I'm going to go to a new panel here, and let's talk about the quotient rule. So our quotient rule, as we have seen in the product rule, things don't work the way you might expect. So the derivative of f of x over g of x, it turns out, is the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Holy smokes. I think we better recite this a little bit. Now you have to start with the denominator. That's important. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. Sometimes you can write this symbolically as the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. That takes a little practice. Let's do a few examples. So let's take the derivative of, and let's do e to the x over x squared plus 1. So this is going to be a quotient rule. So we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And we'll just stop right there for now. Let's do f of x is going to be, let's do x plus 4 over, say, x squared minus 5x. So that means, using the quotient rule, we have the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. And we are going to have to do some simplification and a lot of factoring down the road here. Let me just caution you that because that quotient rule is so involved, many times we want to be careful, and if there's a way we can avoid the quotient rule, that will make our life much easier. Let me do a different one than this. Let's do x squared minus 7x plus 13 all over 4. Now it looks like, we could do the quotient rule here, but because the denominator is really just a number, it's going to be easier to dodge the quotient rule and instead break this apart and make it into separate fractions. So we can call that 1/4 x squared. I haven't done any calculus yet. Minus 7/4 x plus 13/4. So that's still g. We haven't taken a derivative yet. But now we can, without using the quotient rule, find the derivative much easier. 2 times a fourth is a half x to the first, and we'll just get the coefficient when we take the derivative of x, and the derivative of the constant is 0. So that's going to be much simpler that way. We can even do that when we have something like just a monomial denominator. So if we say h of x is going to be x to the third minus 4x plus 5, that's supposed to be a 3, and that's all over, we'll say, x squared. You can use again the quotient rule, but it's going to be easier, I believe, and we want to get skilled at splitting this apart and doing some algebra first before we try to do the derivative. So we can simplify x cubed over x squared is just x. 4 minus 4x over x squared is going to be a minus 4 over x. And we can start getting used to writing the over x as x to the negative 1. And the 5 over x squared we can write as 5x to the negative 2, so it's in a more derivative-friendly form. So now we can actually do our calculus, and the derivative of x is 1. The negative 1 from the exponent multiplies the negative 4 to become 4. Subtract 1 from the negative 1, we get negative 2. The negative 2 exponent multiplies the 5 to be negative 10. Subtract 1 from the exponent is going to be negative 3, and that's going to be quicker and easier than using the quotient rule. So let's do maybe one more. So let's do something like, we'll say j of x will be x over e to the x plus 1. So remember, you can't split up a denominator like we did up here. So there is no great way to do this. So we're going to just have to bite the bullet here and use our quotient rule. So we'll get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. So let's just simplify a little bit up in the numerator. That's just e to the x plus 1, and then we'd write that as a minus x e to the x, and I would not recommend squaring out the e to the x plus 1, but instead leave it like that. So I'm going to go to a new panel, and let's do some numerical examples. So we'll see our functions given as in a table. So I'm going to say x, and then we'll go f of x. I'm going to pause it here and write this down. Okay, so let me move this back down. So we have a table here where we have f, g, and the derivative of f and the derivative of g at a couple of values, x equals 1 and x equals negative 2. So let's see if we can use the appropriate rules here. So we're going to take the derivative of f times g and evaluate that at 1. So first we're going to use our product rule. So we have the first f of x times the derivative of the second plus the second times the derivative of the first. And then we're going to evaluate all of those at 1. So that's going to be f of 1 times g prime of 1 plus g of 1 times f prime of 1. And so now we go to our table. F of 1 we can see is 2, and g prime of 1 is 4, plus g of 1, which is 3, times f prime of 1, which is negative 1. And so we get 8 minus 3, so I believe we get 5 out of that. The second one, now we have to use our product rule. So we're going to get the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator squared. We're evaluating all these at 2, so it's going to be g of 2 times f prime of 2 minus f of 2 times g prime of 2 all over g of 2 squared. So going to the table, those should be negative 2. Sorry about that, because we don't know anything about x equals 2. So I'm going to make these all negatives. So use your imagination here a little bit. Okay, so g of negative 2 is going to be 2, and f prime of negative 2 is 5, and then minus f of negative 2 is negative 2, and g prime of negative 2 is negative 3. And that's going to be all over g of negative 2 squared, so that's going to be 2 squared. So let's see, we have 10, and 3 negatives makes that a minus. 2 times 3 is 6, all over 4. Wow, what are the odds that it works out that nice? Beautiful. Now here we have a product rule. So we are going to get the first, x cubed, times the derivative of the second, which is g prime of x, plus the second, g of x, times the derivative of the first, which is going to be a 3x squared. We're going to evaluate this all at negative 2, so we're going to get negative 2 cubed times g prime of negative 2 plus g of negative 2 times, that's going to be 3 times negative 2 squared. So let's see, we have negative 2 cubed is negative 8, and the g prime of negative 2 is negative 3. And then we're going to get the plus g of negative 2 is 2. And then we have negative 2 squared is positive 4 times 3 is 12. And so it looks like 24 plus another 24 is 48. Okay, so then we're going to do now, we don't know yet how to do a function raised to a power. So the only way we can do this yet, well, this will change shortly, but we're going to have to treat that as f of x times f of x for right now and do a product rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. Or we can recognize that that's really just 2 f of x times f prime of x's. And if we evaluate that at x equals negative 2, then that's going to be 2 times f of negative 2 times f prime of negative 2. So that's going to be a 2, and f of negative 2 is negative 2, and f prime of negative 2 is 5. And so that's going to be negative 4 times 5 is negative 20. Okay, let's do one more panel and one more set of examples. This time I'm going to pause it here and write a function given as a graph. Okay, so we see that in the yellow is our f of x, and in the green is the g of x. These are supposed to be all straight line segments, so don't be confused by my shaky hand there. And they're all at grid points, not trying to be sneaky there and put them at like 1 3/4 or 1 1/10 or something like that. H is the product of f and g, and k is the quotient of f and g. So in part A, we want to find h prime of 2, so h prime of x is going to require us to use a product rule. And so that's the first times the derivative of the second plus the second times the derivative of the first. So h prime of 2 means we're going to get f of 2 times g prime of 2 plus g of 2 times f prime of 2. So now we have to evaluate these on the graph. F of 2, when we go to 2 and up to on the y curve, or on the f curve, that's going to be at 1. So that's going to be 1. Now g prime of 2 means at 2 we want the slope of, since that's a straight line segment, we want the slope of that line, but that's a horizontal line, which means its slope is 0. G of 2 means we're going to go up to the green curve at x equals 2, and that's a y value of 3. F prime of 2 means we're going to find the derivative, the slope of the tangent line, at 2 on the f graph, and since that's a straight line, it's going to be just its slope, which looks like down 2 over 2 is going to be a negative 1. And so that's going to be 0 minus 3, or negative 3. Now for B, we want k prime of 2. So first we are going to have to do k prime of x is the quotient rule. So we have the denominator times the derivative of the numerator. I'd really recommend you say it out loud when you do it. minus the numerator times the derivative of the denominator all over the denominator squared. So evaluating it at 2 means we need all of these values at 2. So I'm going to quickly write all of those in, and then we can go to our table. So again, g of 2 is going to be 3. F prime of 2 is the slope of the tangent line, and we said there was -1. Minus f of 2 is 1. And the g prime of 2 we said was 0. And that's all over g of 2 squared, which is g of 2 is 3 squared. So that looks like -3 minus 0 over 9, I think is a -1/3. All right, very good.